Functions, Lesson 5, the modulus function. So we're going to start off by thinking about what the modulus function actually is. Now, the word modulus can be used to refer to the idea of magnitude, which of course we know means size. So to give you some examples, the modulus function is written like this. So if I want to know the modulus of 3, I write down 3 with 2 vertical lines either side of it. And you will have seen this notation before in your study of vectors when you've talked about the modulus or the magnitude of a vector, and also in mechanics. So the modulus of 3 is equal to 3. The modulus of 2.8 is equal to 2.8. The modulus of negative 4 is equal to 4. The modulus of negative 5.72 is equal to 5.72. And the modulus of 0 is equal to 0, to give you a few examples. So we can think of the modulus as representing the magnitude or the size of a number, irregardless of whether it's negative or positive. So the direction of the number doesn't matter, the size of the number is the important thing. So let's imagine a number line, and on that number line I'm going to mark 0, 1, 2, etc. and then some negative numbers as well. So when we refer to the modulus or the magnitude, we look at the size of a number. So the number 2 has a magnitude of 2 units, which is exactly the same magnitude as a number negative 2. So the modulus of 2 is the same as the modulus of negative 2, and they're both equal to 2. Think about other contexts that you have seen before. For example, you've talked about the magnitude of vectors. Let's imagine we have a vector x, which we will say is 2i plus 3j. So that means it's 2 units along to the right and 3 units upwards in a traditional I and j vector system. Then the magnitude of this vector, or the modulus of the vector, is the length of this line here, which is of course calculated using Pythagoras theorem, which gives us root 13. So always think about modulus as referring to magnitude or size of a value. Now, we can actually write down the modulus function in a formal way. So if f of x is equal to mod x, then this can be expressed as x is just equal to x for any numbers 0 or above. But if x is a negative number, i.e. less than 0, then the modulus of x would equal negative x. Now how does that work? So if x is equal to 3, for instance, it falls into this category, and then the modulus of 3 would just equal 3. If, however, x is in this category, for example, x equals negative 3, then the modulus of negative 3 would equal negative 3, which would also equal 3, which makes sense. 0 could, in theory, go in either category because 0 is neither positive or negative, but for conventional reasons it is grouped with the positive numbers. So let's sketch the graph of the modulus function. Here we have a set of values. Let's label the x and y axes. So for values of x that are greater than or equal to 0, the modulus function simply equals x. So it looks like a portion of the graph y equals x, a straight line like that. So you can see that the value 3 links up with a y value of 3. So y is equal to mod x. Now, for the values on this part of the x-axis, i.e. negative values, f of x is equal to negative x, which means we have a portion of the line y equals negative x. So the whole function together looks like this. If we pick a value negative 3, it would match with y equals 3 on the y-axis. So the graph has a V shape. You can have a go at plotting this on your graphical calculator. In graph mode, mode number 5, as you input your graph, press Option, OPTN, and then press F5, which should say something like numeric or num, and then F1, which is abs. Now, abs stands for absolute value, which refers to the concept of a number having an absolute value or magnitude regardless of direction. So the absolute value of 3 is 3, and the absolute value of negative 3 is also 3. So we ignore the direction of a number, whether it's positive or negative becomes irrelevant. We look at the actual size of the number. So you can use this to plot a graph of y equals mod x, and you will find that you get this V shape as we've sketched here. So this portion of the graph would have the equation y equals x, and this portion of the graph would have the equation y equals negative x. And you can see there are no negative y coordinates, because the whole concept of the modulus function is that it returns the absolute value or the size of a number. So we're going to start off by exploring some transformations of the modulus function. The graph is sketched in the top right-hand corner, so you have that to look at as a reference point, and you can try out each of these transformations on your graphical calculator after we've sketched them through, so you can see and confirm for yourself that these are the shapes of the transformed graphs. So, example number 1, we're going to start off by exploring the graph of y equals mod x plus 2. Now, let's think about transformations. If our function y equals mod x is the original f of x, then what we're looking at is f of x plus 2. And having studied earlier transformations of functions, we should know very clearly that this is a translation with the vector of 0, 2, i.e. a shift 2 units upwards. So our graph will look a little bit like this. Here's one portion, and here is the other portion. It should be a perfect mirror image of each other. So this is the graph of y equals mod x plus 2, and of course this coordinate here, 0, 2. We're now going to have a look at a second example. We're going to sketch the graph of y equals mod, and then inside the modulus sign, x plus 1. We're going to actually look at doing this in 2 different ways. So method 1 is going to involve using transformations, and method 2 is going to involve us thinking about the modulus function in a bit more detail. So method 1, remember, we're calling y equals mod x our original f of x, and we should be able to see from our work on transformations of functions that this is f of x plus 1, because the modulus is being applied to all of x plus 1. So we know that this is a translation, and we know it's with a vector of negative 1, 0, which means the function will be shifting 1 unit to the left. So it will look like this. -1 here, and it will cross the y-axis at 1. Now, how can I double check that? Well, y equals mod x plus 1 is the equation of the curve. If I allow x to equal 0, y then equals the modulus of 0 plus 1, which is the modulus of 1, which of course is 1. So I can just calculate a y-coordinate. And there, the sketch is complete. But let's have a look at the second method, which is also very interesting. I start by sketching y equals x plus 1, which is the function inside the modulus. Now, y equals x plus 1, very simply, looks like that. Crosses the y-axis at 1, crosses the x-axis at -1. Now, the modulus function takes anything that's negative and effectively makes it positive. That's one way of thinking about it, which means this portion here has got to be reflected in the x-axis so it becomes positive, which means we simply take that red dotted part and reflect it upwards like that, which creates the graph of y equals mod x plus 1. So we start by sketching y equals x plus 1, the function inside the modulus. Then we reflect any parts of the graph that are below the x-axis in the x-axis. And really, I should get rid of or dot out this part here. So we only have the actual final answer. So let's have a look at a third example. We're going to sketch the graph of y equals mod 2x plus 3. We're going to use both methods again. We'll start with the method 1, which involves us using transformations. So we can see this is the transformation y equals f of 2x plus 3. Now, a few alarm bells should be ringing here because this is one of those transformation combinations of the form ax plus b. And if you've remembered this very carefully, you will be aware that it is the translation that occurs first of all and then the stretch. Go back and refresh your memory on this if you have forgotten. So the order in which these transformations must take place for our example is we need to have a translation with a vector of -3, 0 first of all, which deals with this part of the transformation. And then the second transformation that we need to enact is a stretch in the x direction with a scale factor equal to 1/2, which performs this part of the transformation. So we're going to do this in 2 stages. We're going to sketch the translation first of all over here, which will give us the graph of y equals mod x plus 3. So we know that's a translation with a vector -3, 0. So this gives us a graph that looks like this. We're then going to sketch the second part of the transformation, so from here to here, which is going to give us the final answer of y equals mod 2x plus 3. Now, it's a stretch in the x direction with a scale factor of 1/2, which means that our x coordinates must multiply by 1/2, but our y coordinates must stay the same. So that means this coordinate, which was -3, 0, will become -3/2, 0, and our graph will stretch like this. This coordinate here will stay as 0, 3, because of course 0 multiplied by 1/2 is still 0, and this is our final answer. So let's approach this with method 2 now, where we just use the idea of the modulus function. So I'm going to start by sketching y equals 2x plus 3. Now y equals 2x plus 3 will look like this. Straight line with a y-intercept of 3. And of course it's going to have an x-intercept of negative 3 over 2, which we can work out very easily. Now again, I need to take this portion here, which falls under the x-axis, and I need to reflect it upwards using the x-axis as a mirror line. So this is my mirror line there, and this then completes our graph. So we started by drawing y equals 2x plus 3, which was the original line, but we now have completed the modulus function. And I can remove or dot out this portion here, which is no longer required. Now, both of these methods for sketching transformations of y equals mod x are equally valid. You're going to have a go at 6 examples. You can use either method, whichever one you prefer. You may want to try using both methods in each example and then coming to a conclusion about which method is a little bit easier to use. In question number 4, you may find it easier to think of this as y equals negative mod x plus 5, as it's a little bit easier to sketch that way and to think about the transformation that way. You may find that in some methods the transformation approach is a little bit easier. In other questions, actually, it's the sketching of the original function and then applying the modulus that is a little bit easier, so method 2. The whole point of mathematics is to be versatile in the methods that you choose and understanding that different methods can be better in different situations. When you've sketched each of these, check it using your graphical calculator. Check that you have got the x-intercepts and the y-intercepts correct as well, and make sure your graphs are fully labelled. We're going to move on to exploring how we solve equations using the modulus function. We're going to start off with a simple example and then build up to more complex examples, and we're also going to explore 2 different methods as well. So method 1 will involve using some algebra. Let's look at the equation that we're going to solve. Mod 2x plus 1 equals 5. Now, if the modulus of 2x plus 1 equals 5, that means the magnitude of 2x plus 1 must equal 5, which means that 2x plus 1 must equal 5, or 2x plus 1 must equal negative 5, because negative 5 would also have a modulus of 5. And the answer to the question is, which values would give us a modulus of 5? 5 or negative 5 are the 2 possible answers. We can then solve each of these very simple equations. So x is going to equal 2 in this example, or x here is going to equal negative 3. And we have 2 answers to the question, found using the algebraic approach. Let's now have a look at the second method, which involves using graphs. So I've sketched in advance the graphs of y equals mod 2x plus 1, which is the left-hand side of our equation, and then the right-hand side of our equation, y equals 5. You can sketch this by hand now that we've looked at performing the transformations. You can also sketch these on your graphical calculator or using the Desmos software or using the Autograph software or another graph drawing package. And you can see that there are 2 intersections. Now, having solved the equation algebraically, this makes sense. Let's have a look at the 2 points of intersection in a little bit more detail. I'm going to call this one A, and I'm going to call this one point B. Now, at point B, we know that this portion of the graph, which I'll highlight in green, like that, is the graph of y equals 2x plus 1. And that is equal to 5. So at B, we're solving the equation 2x plus 1 equals 5, which of course gives us x equals 2, which we've seen before. Now at A, something a little bit different is happening. At A, this portion of the graph is the line y equals negative 2x plus 1, like that, or y equals minus 2x minus 1. You can see that. Imagine tracking this graph backwards. You can see it would cross the y-axis here at negative 1, and you can also see its negative gradient, like that. So y equals 2x plus 1, but the negative version of it. Now that, of course, is equal to 5. So solving this, negative 2x minus 1 equals 5. Negative 2x equals 6. X equals negative 3. And we can see that we have the second point of intersection. So A has got coordinates negative 3, 5. B has got coordinates 2, 5. So the answer to the actual equation, x equals negative 3 or x equals 2. And there are two different approaches here. Now, you may be thinking, well, the algebraic approach is a lot quicker and a lot more efficient than the graphical approach. But we will see, as we look at some further examples, exactly why the graphical approach is so important to what we are doing. So let's look at a second equation. It is a little bit harder. This is in fact example 2, not example 1. So we have the modulus of 2x plus 1, which is equal to x plus 4. We're going to do this in 2 stages. Again, we're going to look at method 1, involving algebra first of all, and then method 2, using a graphical approach. So using algebra, we know that 2x plus 1 could simply be equal to x plus 4 as one option. If we then solve this, we get x equals 3. Very quickly, very easily as one possible answer. Of course, the other option is that 2x plus 1 is equal to the negative of x plus 4. Solving this equation, we then find that x is equal to negative 5/3. So we get two answers to the equation. Now let's explore exactly the same equation using a graphical approach. Again, I've pre-sketched the graphs we need here on this set of axes. So this red graph is the graph of y equals modulus 2x plus 1. And the blue graph is the graph of y equals x plus 4. Now, there are 2 points of intersection. Let's label them again. So this is point A and this is point B. Now, at point B, this is where this portion of the graph is just the graph of y equals 2x plus 1, and it meets the blue line x plus 4. We can then solve this, and it simplifies down to give us x is equal to 3, which we've seen before. Now at point A, however, we're looking at this portion of the graph, which is the graph of y equals negative 2x plus 1. And again, if I expand that, that's the graph of y equals negative 2x minus 1. Again, imagine that portion tracking back. You can see its y-intercept of negative 1, and you can see its negative gradient as well, gradient of negative 2. That is equal to the graph of y equals x plus 4 at the point A, because there's an intersection, and we can then solve this equation. So negative 2x minus 1 equals x plus 4. Keep rearranging it. 3x is equal to negative 5. X is equal to negative 5/3, which again we've seen over here. So the two answers to this equation are x equals 3, the root at point B, and x equals negative 5/3, the root which is at point A. And again, both methods worked very well. There's a bit less algebra involved in the algebraic approach. The graphical approach involved us thinking a bit more, but the graphical approach allows us to see what is actually happening without just performing some algebraic steps without thinking about them. And this is going to be crucial in the third example, which is the hardest example. So, example 3, let's take a look at this equation. So, we will attempt this using algebra first of all. So, let's start off with half x take away 1 equals 2x plus 3, exactly the same approach we've used for the two previous examples. Now, if I rearrange this, I get 3 over 2x is equal to negative 4, and x is then equal to negative 8/3, which gives me one answer. I then do what I've done previously. A half x take 1 is equal to negative 2x plus 3 in brackets. So let's solve this. A half x minus 1 equals negative 2x take away 3. 5 over 2x is equal to negative 2. X is equal to negative 4/5. And we have a second solution, second answer. Now, let's have a look at the second approach here, the graphical method. We have our axes set up with the graphs of y equals mod a half x take 1 in red, and the straight line y equals 2x plus 3. Now, the first thing that you should notice is there's only one point of intersection over here, which we'll call P, which means there is only one answer or root for the equation up here, which means one of these two answers, here or here, is actually a false answer. So this is why using the algebraic approach blindly without sketching a graph can cause some real problems. It can result in the creation of a root which actually isn't correct. Now, how do we know that the graphs will only intersect once? Well, the graph of y equals mod a half x minus 1 in red is composed of this arm, which is a graph of y equals a half x minus 1, and this arm, which is y equals minus a half x minus 1. Now, the gradient of this portion here is a half, as you can see very clearly from that. The gradient of the blue line, y equals 2x plus 3, is 2. So in this portion of the set of axes, you have a graph with a gradient of 2 and a graph with a gradient of a half. They are never going to intersect in this region that I've highlighted in yellow because the blue graph is so much steeper than this red portion over here. The only intersection that occurs is the intersection of y equals 2x plus 3 with the other wing of the modulus function over here. So at P, we know we have a graph of 2x plus 3 intersecting a portion of the modulus graph, which is negative a half x minus 1. Let's solve this. 2x plus 3 equals negative a half x plus 1, which gives us 5 over 2x is equal to negative 2, x equals negative 4/5. And that is the only correct answer. So it tells us very clearly that this part was correct, but this part created a false answer. So the only answer to the actual equation is x equals negative 4/5. And there is only one root. And it's clear that we knew this because we sketched the graph before we went blindly into the algebra without thinking. So in general, when you are solving an equation that involves the modulus function, sketch a graph first before you start doing any algebra. And don't forget you've got your graphical calculator, which will help you sketch the graphs quickly, check how many solutions there are, and it will also allow you to verify that your answers are in fact correct. One last useful thing to remember: if this black graph here is a sketch of the graph y equals mod ax plus b, then this portion of the graph here, which I've highlighted in green, is part of the equation y equals ax plus b. And then this portion of the graph here, which I've highlighted in yellow, is part of the line with equation y equals negative brackets ax plus b. And that can help you solve various equations if you know the equation of each wing or each arm of the graph. So we're now going to explore how we might move from solving equations to solving inequalities that involve the modulus function. In each case, we're going to sketch a graph. You can use your graphical calculator to help you with this. The graphs are pre-drawn in order to make this process a little bit quicker. So, example 1. Notice we are not solving mod x plus 2 equals 7. We are solving mod x plus 2 is less than or equal to 7. So, first key point, we need some sketches of graphs. So on the right-hand side, in green, we have the graph of y equals mod x plus 2. Check it on your calculator again. And we have a horizontal line, y equals 7. And it's clear we've got 2 points of intersection. We'll call them P and Q. And useful for us to know the equations of each wing or each portion of the graph. Now, this portion of the graph is the line y equals x plus 2, and this portion of the modulus graph is part of the line y equals negative bracket x plus 2. Now, in order to solve the inequality, we need to know the coordinates of P and Q, or the x coordinates of P and Q. So that's the first thing we're going to do. We're going to find P and Q, solving equations in order to do so. So at the point Q, we know that the line x plus 2 is equal to 7, which then gives us x equals 5. At the point P, we know negative x plus 2 in brackets must equal 7, and then solving this very simply gives us the answer x is equal to negative 9. So this point here has an x coordinate of negative 9. This point here, Q, has an x coordinate of 5. Remember what we are trying to solve. X plus 2, the modulus of, is less than or equal to 7. So we are looking for the x coordinates which result in our modulus function, the green function, falling underneath the straight line where y equals 7. And of course, that refers to this portion here, which I'm shading in yellow. Now, the x coordinates which will achieve y coordinates which fall within this region are such that x is less than or equal to 5, greater than or equal to negative 9. And we know the equality is allowed because of the equality in the original question up here. And this is our solution. Let's have a look at another example. So this time we are solving modulus of 2x minus 1 is greater than 6. We have some graphs sketched again. Here's the graph of y equals mod 2x minus 1. And here's the graph of y equals 6 in orange. Now, we're going to label each wing of the graph. So this portion of the graph has the equation y equals 2x minus 1, and this portion of the modulus function has the equation y equals negative brackets 2x minus 1. Let's look at the 2 points of intersection, P and Q again. And we know that we can solve two equations to find the coordinates of P and Q. So at Q, we know we have the graph of 2x minus 1, which is equal to 6. So solving this simply gives us an answer of x equals 7 over 2. So this point here has an x coordinate of 7 over 2. And at point P, we're solving negative 2x minus 1 equals 6. And we can simply rearrange this, so negative 2x plus 1 equals 6. X is equal to negative 5 over 2. So this point here, just about fit it onto the x-axis, has an x-coordinate of negative 5 over 2. Now, go back to the original inequality. We want the modulus of 2x minus 1 to be greater than 6. So we are looking for this portion and this portion of the graph which are above the line y equals 6, which means we want these x values and these x values. So our solution set is x is greater than 7 over 2 or x is less than negative 5 over 2. Again, we have no inequality, we have no equality this time because, of course, in the original question, there's no equality there. Now, we can also write this using set notation. It's a good opportunity to practice that and recall our knowledge of set notation. So we would say x is such that x is less than negative 5 over 2, or, so we use the union symbol. Make that clear, that says union. X is such that x is greater than 7 over 2. Example 3, which is a slightly harder question, as you will notice. 6 take away the modulus of 1 minus x is greater than negative 2. Well, we're going to instantly start off by rearranging this because it does not look pleasant in this format. So I can say that 6 is greater than negative 2 plus 1 minus x, the modulus of. Then let's add the 2 across, so 8 is greater than the modulus of 1 minus x, or a little bit easier to write it out as 1 minus x is less than 8. And there we have it. So the graphs have not been pre-sketched here, so we are going to do this ourselves. So I'm going to start off by thinking about what would the graph of y equals 1 takeaway x look like. Well, it's got a gradient of negative 1 and a y-intercept of 1, so it would look like this. But of course I want the modulus, so I want to reflect up this negative portion, and there I have the correct answer. And what I'm going to do is just remove this portion here. There, we have it. So we then want to draw on the graph of y equals 8. Notice this is not to scale. So there's the graph of y equals 8, and there's 8 on the y-axis. Let's label the two wings of my graph. Now this wing here has the equation y equals negative 1 minus x, and this wing here has the equation y equals 1 take away x. How do I know which is the right way round? Well, look at this portion over here, which I'll highlight in red, and you can see it's got a negative gradient and a y-intercept of 1. So it's got to match this equation over here, y equals 1 take away x, whereas this portion here has a positive gradient, and you can see it's going to have a negative y-intercept of, well, -1, if you think about the reflection in the x-axis. Now, if I just expand this bracket here, -1 plus x, and then you can see that matches that line. Remember, you've got your graphical calculator as well to help you draw the graphs efficiently. So let's look at the 2 points of intersection again. There's one here, we'll call it P. There's one here, we'll call it Q. And we're going to find the x-coordinates of P and Q. So starting off with P this time, we know that we're solving 1 minus x is equal to 8. So that simply gives me x is equal to -7. And then at point Q, I'm solving -1 minus x equals 8, which simply gives me x equals 9. Now, I want to solve this inequality here. Remember, we've rearranged the inequality to this. So don't go back to the original question. Go back to the version you rearranged it to, because this graph here matches the graph that we have sketched. So we want to be less than 8 according to this, which means we're looking for the x values between -7 and 9, because they give us this region here. So our solution set is x is less than, there's no equality here, less than 9 and greater than -7. For our next example, we've got a slightly harder inequality to solve in that one side of it actually involves x as well, so it's not a single horizontal line drawn on our graph. The graphs have been sketched again already for us. Let's label each wing of the modulus function. So this arm here is y equals 2x plus 1. Look at its positive gradient and its y-intercept, which is also positive at 1. And this arm of the graph is going to be y equals -2x plus 1, which you can see has a gradient of -2, and if you expand the bracket, a y-intercept of -1, which would match if you tracked that back down here. Now, let's mark on our 2 points P and Q again, and we're going to find the x-coordinates of P and Q, as we've done in the last 3 examples. So let's start with Q. So at Q, we know that the graph of 2x plus 1 is equal to the graph of x plus 2. So solving this very simply gives us x equals 1. So this point here has an x-coordinate of 1. At point P, we then know that -2x plus 1 must equal x plus 2. And let's rearrange this. So this gives us 3x is equal to -3. X is equal to -1. So a nice piece of symmetry here. So we're then trying to solve, and we didn't rearrange the original question, where the modulus function is less than the straight line y equals x plus 2. So we're looking at this enclosed region here. We're looking at the x-coordinates that create that region. So it's very, very simply x is less than 1, x is greater than -1. Now, it's important that we actually understand what inequalities involving the modulus function actually mean. So let's take an example, very, very simple. Mod x is less than 2. What does that actually mean? It means that x has to be a number whose magnitude, whose absolute value, whose size is smaller than 2, regardless of whether that number is actually negative or positive. So a good way of thinking about this is to think of a number line. Let's mark on some numbers onto said number line. So we've got 0, 1, 2, 3 and onwards, and some negative numbers, -1, -2, -3, etc. Now, we want the magnitude of x to be less than 2. So that means we're looking at all these numbers here between 2 and negative 2, but not including 2 or negative 2 because it's a strict inequality. So mod x less than 2 means that x is between 2 and negative 2. And it's important that we understand that. What happens if the inequality is a bit different? For example, mod x is greater than 2. What does that mean? Well, let's have a look at our number line again. Let's label it like last time. This time, we're looking for numbers which have a magnitude, a size, an absolute value which is larger than 2, irrespective of whether the number itself is negative or positive. So that means we're looking at any number which is above 2 and any number which is more negative than negative 2. Because, of course, the modulus of negative 3, for instance, would equal 3. And that's clearly bigger than 2, which means negative 3 would be included. So this time, interpreting the inequality, mod x is greater than 2 means that x itself must be larger than 2 or x must be less than negative 2. Now, we can generalise these. If we have mod x less than a, that tells us that x is between a and negative a. If mod x is greater than or equal to b, this tells us that x is greater than or equal to b, or x is less than or equal to negative b. Now, if mod of x take away a is less than b, this tells us that x minus a must be less than b or greater than negative b, essentially applying the logic that we've seen here and here in these examples. If we then add a to all parts of this inequality, we then have x is between a minus b and a plus b. And we're going to use this idea in our next example. So express this inequality in the form of a modulus inequality. So I'm actually going to start with the modulus inequality here. Mod x minus a is smaller than b. Now we know from what we've looked at previously that this means that the number inside the modulus, the x minus a, must be less than b or greater than negative b. Add a to all parts of the inequality, which means that x must be less than a plus b but greater than a minus b. And we're comparing this with this inequality here. Because if we find out what a and b are equal to, then we can rewrite this inequality over here in this format over here. So if we compare the two parts, we can see that we have a minus b must equal negative 3. And then if we compare these parts over here, we can see that a plus b must equal 9. And we have a very, very simple pair of simultaneous equations, which can be solved extremely easily. Let's write them down clearly. A minus b equals negative 3, a plus b equals 9. And if we very simply add these together, we have 2a equals 6, so a is equal to 3. Substituting back into any of these equations simply tells us that b is equal to 6, so that tells us that this original inequality can be expressed as the modulus of x take away 3 is less than 6, by using our values of a and b and substituting them into this result here.